We are now going to look at the tetrahedral intermediate. This particular compound is called an ester. The functional group of an ester is a carbon which is double bonded to an oxygen, and that same carbon is bonded to an OR group. So this is the functional group of an ester. It happens to have as a substituent a benzene ring. We will look at benzene rings in greater detail later. But this is the benzene ring, and when the benzene ring is a substituent, it is called a aryl group, or more commonly a phenyl group. Because it's called also a phenyl group, it's sometimes symbolized as pH as for a phenyl group. So I'm going to stop drawing this because I have difficulty drawing, and I will put a pH every time the phenyl group comes up. Nonetheless, so here's the reaction with NaOH and alcohol. So if you were to see this reaction, hopefully by now, the first thing that you would say is, okay, if this is in reaction, we have Na plus OH minus. And then right off the bat, you would say, sodium is just going to hang around. It's a spectator ion. It's not getting involved in the reaction until the very, very, very end. Then there's OH minus, great nucleophile, and it is fully charged. Then there is alcohol in solution, ETOH. The oxygen is delta negative. However, if something's going to be reactive in this reaction, it's going to most likely be the thing which is most highly charged, and that's the OH minus. In other words, the delta negative charge on the oxygen here is no match for the formal negative charge on the oxygen here. Therefore, this would be most reactive. And in terms of looking here, well, we have delta negative oxygens, and then clearly this carbon here, which is attached to not other than two oxygens, one here and one there, this carbon here must be very delta positive because of oxygen withdrawing electrons being more delta negative in two spots. So this negative charge will be attracted from the OH minus to this delta positive carbon, hitting this delta positive carbon and therefore breaking the weakest bond, which would be here, knocking it up like so. So then we have OH minus attacking here, attached to this carbon, and then electrons being knocked up this way. So our intermediate would look something like this. It would be our phenyl group here, and then this would be attached to our carbon, the oxygen, knocked up its electrons. Then we have down here the OH group, which just attached, and then we have the OCH3 group over here. And so this is what is called the tetrahedral intermediate. First of all, it's the intermediate in the reaction because the reaction is not over. And second of all, carbon is in the center of a tetrahedron. And all that means is that carbon has indeed 4 bonds. Anytime carbon has 4 bonds, it is in the center of a tetrahedron. So here is our tetrahedral intermediate. A tetrahedral intermediate is extremely unstable. Therefore, a reaction is going to occur very quickly. There's too much oxygen around here, too many delta negative competing factors, all of them pulling electrons to himself. But then carbon is delta positive. It's very delta positive, on top of which there's a lone pair of electrons right there. And we said before, intramolecular reactions happen very quickly in comparison with intermolecular reactions. So here we have a negative charge. Here we have a delta positive carbon. Clearly, this is going to be a very quick reaction in which this is going to want to come down and hit this carbon as quickly as possible. But if it were to come back down, somebody's got to go. Well, will it be the phenyl group? This is a carbon-carbon bond. Very strong. Carbon-carbon bonds are very strong because it's equally shared. But here are 2 bonds which are unequally shared because oxygen is drawing electrons to itself. So basically, both of these are not good leaving groups, as opposed to halides, which we saw before, are excellent leaving groups and would be the first to go. Both of these are not good leaving groups, but of the two, the best of a bad bunch would be the OCH3 group, which would be forced to leave, and so we would have the electrons come down, the OCH3 group would leave, and then we get our phenyl group attached to the carbon. Now it's double bonded because the electrons have come down and attached to the carbon, and this is attached to the OH group. Then we have plus OCH3, and this is negatively charged. Actually, there was once an MCAT question very similar to this one, and it asked what was the result of a particular reaction, and then they had as a possible answer something similar to this as a possible answer. And so I'm sure many students felt great that they had accomplished the problem, they'd gone through all the steps, delta negative, delta positive, everything, and then they were finished and they were happy, and then they didn't get it right because the reaction is not over. Because once you see this reaction as it is, you should be able to look at this part of the reaction and recognize what this is. This is a carboxylic acid. So this is a carboxylic acid, which we know is a proton donor. And this is a compound which would love to have a proton because it has its negative charge. It's not particularly stable compound. It would love to have a proton. It is a proton acceptor, and therefore it is a base. And you may remember from general chemistry that whenever you have an acid plus a base, you get a salt and a neutral compound. So this is an acid plus a base. So our salt would be the product after this proton is given off. We get pH, C, double bond to the oxygen, O minus, and sodium floating in solution. So that brings us our salt, Na plus, and then this is plus HOCH3. So this is our neutral compound, which is methanol. And here is our salt. So we have an acid plus a base, gives you a salt plus a neutral compound. So we've come to the final conclusion of this particular reaction. But the whole reaction is based on electronics and very basic rules of organic chemistry. We are now going to look at amides. The functional group for an amide is the carbon double bonded to the oxygen with the carbon also bonded to the nitrogen. There are a couple of features which are very important to remember about amides. To begin with, the nitrogen, as we know, when the nitrogen has 3 bonds, it has a lone pair of electrons. Now, when we look at the resonance structures, remembering by looking at the periodic table that oxygen being to the right and high up, and oxygen is more electronegative than nitrogen. Nitrogen is electronegative, but oxygen is more electronegative. Therefore, oxygen will draw electrons to itself. So as oxygen draws electrons to itself, we can envision these lone pair electrons in the nitrogen being attracted to this delta positive carbon, these electrons going into this bond, forming a double bond between the carbon and nitrogen, then breaking the pi electrons up here and sending these up to the oxygen, and oxygen is very happy with that because it gets these lone pair of electrons. So then we can imagine that one of the resonance structures that we can write for this compound would be R bonded to carbon, oxygen with its lone pair, double bonded with the nitrogen, and then we have R prime, R double prime. So we can imagine that this is one of the resonance structures that could be suggested for this particular compound. Now, of course, this would be negatively charged and then this would be positively charged because it gave up its electrons and the overall molecule was neutral to begin with. Well, as we know, these two compounds are not resonating back and forth. There's actually some sort of way in which those lone pair electrons are actually delocalized between the oxygen and the nitrogen. So if we were to just draw that, R prime and R double prime, then we would write that this is sort of a bond here, but this is delocalized electrons going up like this, where this is, very delta negative, and this is a delta positive nitrogen because it's giving up its lone pair of electrons into this bond where it's sort of delocalized along this area. Well, a couple of things to say. First of all, when we started organic chemistry, we talked about conformation, and that is free rotation about single bonds or sigma bonds. And so we would have expected that there would be free rotation between the carbon and nitrogen. However, we don't get to see that in this compound. There is restricted rotation. It means it's possible that there could be rotation, but it is very difficult to rotate among the carbon-nitrogen bond because it's not a simple single bond, because the electrons from the nitrogen are partly delocalized, and so it's not a simple single bond, and therefore there's not free rotation here. So that's one important point to remember about amides. The second important point to remember about amides is that the lone pair electron on the nitrogen is not available for bonding as it usually would be. For example, when you look at ammonia, NH3, which has lone pair electrons, we have NH3 like this. It has lone pair electron. When we add a proton, H+, the proton adds to those lone pair electrons, and that produces NH4+. So this is the ammonium ion, and that's produced as a result of the lone pair electrons on the nitrogen. However, the lone pair electrons on the nitrogen of an amide are not available for bonding as you would get in most compounds with nitrogen, because the lone pair is involved in this delocalization. Now we will look at a common type of MCAT question based on this concept. So my question to you is straightforward. Which of these following chemicals is nitrogen serving as the strongest base? So in which of these chemicals is nitrogen serving as the strongest base? Perhaps you may want to pause and consider what you would provide as a response. So let's work it out. Here clearly is an amide. It's carbon double bonded to oxygen where the carbon is bonded to a nitrogen. That is the functional group. Amides, as we've seen already, the nitrogen is not available for bonding. So what's the importance of that? Well, if they're asking where does nitrogen serve as the best base, well, one of our definitions of base is that a base is a proton acceptor. So if you have something which is going to accept a proton, which is positively charged, clearly the nitrogen must be negatively charged, or at least partially negatively charged. So we would be looking for the nitrogen, which has the greatest partial negative charge. The more the partial negative charge is, the more it would attract a proton, the stronger base it would be. In other words, we take their question, then we translate it into language which is practical so that we can look for something on a practical basis. The most delta negative nitrogen, which is obviously a much more simple concept than just thinking, well, what's the strongest base? Okay, we're looking for the most delta negative nitrogen. Well, we've already seen that the nitrogen in an amide is delta positive because its lone pair electrons is involved in a resonance structure or delocalization of the electrons. And so this would be a decidedly poor base. It would be very poor in attracting a proton to that nitrogen. So this A is definitely out of the question. Then we have ammonia. And we know ammonia has a lone pair of electrons, and therefore it would be very attractive for a proton to land on ammonia, producing NH4, the ammonium cation. So yes, definitely ammonia would be a very good base. So then we have this compound. We have a methyl group, which is an R group, attached to the nitrogen. In what way will this affect the delta negative aspect of this nitrogen? Well, because there's a methyl group attached to it, and we know by definition alkyl groups are somewhat electron donating, meaning that compared to just having a hydrogen, because there's this alkyl group, it is somewhat electron donating. That means it will make this nitrogen even more delta negative than this one. And then here we have a nitrogen with two methyl groups attached to it. That is, two alkyl groups attached, both of them being somewhat electron donating, somewhat donating electrons to this nitrogen. Therefore, this nitrogen indeed would be the most delta negative of them all because of the alkyl groups, which are inducing it to be even more delta negative than it would be in ammonia. Therefore, the correct answer would certainly be D. Amino acids. Amino acids are called amino acids because they have the amino group, NH2, and there is the carboxylic acid group, so it's called amino acids. Obviously, amino acids are extremely important. We've discussed that in biology. They are the building blocks of proteins. In fact, the 20 naturally occurring amino acids are called alpha amino acids. The reason is when you see a carbonyl group in organic chemistry, the carbon next door to the carbonyl group is called the alpha carbon. The next carbon over is called the beta carbon. So this is the alpha carbon. The amino group is attached to the alpha carbon, so these are called alpha amino acids. Just as an aside, the alpha hydrogen, meaning the hydrogen attached to an alpha carbon, is slightly acidic. Nothing compared to carboxylic acid, of course. This is seriously acidic for organic chemistry. Not at all acidic compared to general chemistry like HCl, H2SO4. But among organic chemicals, this is acidic. And so, of course, this group is basic. And a molecule that has this acidic and basic component within the molecule is called amphoteric. The other thing that we can say about amino acids is that they are chiral. This central carbon is attached to 4 different groups. Hydrogen, carboxylic acid over here, R group, and an NH2 group, the amino group. 4 different groups, therefore it is chiral. In other words, it is optically active. So all amino acids are optically active, except for the smallest of the amino acids called glycine. And glycine, the R group, is a hydrogen. So it's not optically active because it's an achiral compound. You don't need to memorize the names and the R groups of all the different amino acids. That would be a terrible waste of time. And as you get practice doing MCAT problems, you'll see that's not the type of question they like to ask. We'll look at the kind of common questions they like to ask. But in general, you should know that a lot of the features of an amino acid is dependent on the R group. If the R group is a fatty group, you know, with no charged particles, it can create a hydrophobic or afraid of water type of amino acid. And if the R group is charged, it's polar, it's acidic or basic, then because of that, it can create a very polarized amino acid, and it would be hydrophilic, because we know that polar molecules like to interact with water. So hydro is water, philic is loving. So water loving would be if this is charged or polar. Hydrophobic, or afraid of water, would be if this is a very fatty type of R group. So in fact, it's the same thing as when we discussed the plasma membrane in biology. The hydrophobic part of the plasma membrane is on the inside, afraid of water, and the hydrophilic part is on the outside of the membrane, interacting with the intracellular part or the extracellular part where there's lots of water. Same thing with proteins, because we know proteins are made from amino acids. And so the protein itself, the interior of the protein will have the more hydrophobic type amino acids, while the exterior part of the protein will have the more hydrophilic type amino acids. Now, when you see an amino acid in solution, it doesn't generally look like this. The reason is we know this is acidic. We know this is basic. Remember, there's a lone pair of electrons on the nitrogen. It can accept a proton. And this can clearly give a proton, and therefore we have our resonance structure and stabilized carboxylate anion, and we have the amino group that can accept a proton. So when this is really in neutral form, this is an anion with the proton kicked off, and this accepts the proton, so it is positively charged. The idea that the molecule has a negative and positive part shows that it is a dipolar molecule in its neutral form. And that is called a Zwitter ion. Now, the common question they like to ask on the MCAT is regarding pH changes for the Zwitter ion. Meaning, if this in its neutral form is going to be negative because it's acidic, and this in its neutral form is positively charged because it's basic, it can accept the proton, how do we determine when it will be neutral, and when, for example, when there's more hydrogen ions around, meaning a lower pH, then this will be protonated, and this remains NH3+. But when there's no hydrogen ions around, so the pH is very high, so there's very few hydrogen ions around, therefore this will kick off its proton, and this will even kick off its proton. And then the overall charge of the molecule will be negative. So how do we know when the overall charge of the molecule will be positive, or overall negative, or overall neutral? That we determine by the isoelectric point. And this is very simple. The idea is as follows. You may remember from general chemistry that the acid dissociation constant, Ka, allows us to know how much dissociation of the acid occurs. So this is going to have a Ka value. This will have a Ka value. So it tells us how much this would be able to dissociate a proton. And we have a Ka value for this as well. Well, if we take the pKa of this plus the pKa of that, we add them together and divide by 2. In other words, we're looking at the molecule, and we want to take the average pKa values of the parts of the molecule that can dissociate. If we take the average of those values, then we get the isoelectric point. In other words, we get the pH at which this overall molecule will be neutral. Now, even when it's neutral, it doesn't look like this. This is what we draw in organic chemistry as shorthand. But the reality is, when it's neutral at its isoelectric point, this will kick off the proton, and the proton will be attracted to the delta negative nitrogen with its lone pair of electrons, which we know to be a basic part of the amino acid itself. So this is the acidic part, and this is the basic part. So, and the isoelectric point will be the dipolar amino acid or the Zwitter ion. At any pH above the isoelectric point, meaning it's a higher pH, there's going to be less protons around. So at any pH above the isoelectric point, this will be overall negative, less protons available. At any pH below the isoelectric point for this amino acid, whatever amino acid in particular, any pH below the isoelectric point means there's more protons available. So this will be protonated and this will be protonated, overall charge positive. That's the type of question they like to ask on the MCAT. Now, let's make a protein. So here we have our amino acid, and here we have another amino acid, say a neighboring amino acid. And so we have the amino group NH2, delta negative nitrogen. We have our delta positive carbon in the carbonyl group. So this will be attracted to the delta positive carbon, opposites attract, hits the carbon, knocks up the electrons, and then blah, blah, blah. The exact mechanism you do not need to know for the MCAT. But essentially, you do need to know the basics, and that is to create this bond, there's an attraction between the nitrogen and the carbon, and then what happens, it's as if a hydrogen here and the OH group, hydrogen and OH create water, and then the water leaves, and then this bond is possible. When you look at this, this is an amide. Remember, nitrogen bonded to the carbonyl group. So this is an amide, so this is called an amide bond. In this context of making a protein, it is also called a peptide bond. Now, the water was kicked out. When water is kicked out, that is called a condensation reaction. You can sort of think of it as when there's water vapor in the air and it starts going onto the window or something. It condenses, there's condensation, so water is kicked out of the air and goes into another form. So when water is kicked out of the reaction, that's called condensation. If you were to take a water molecule with its delta negative oxygen, it would be attracted to this delta positive carbon, hit it, and blah, 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 reverse reaction occurs. So you end up with the OH group here, and it separates. That's called hydrolysis. So this reaction would be called condensation, and the reverse direction would be called hydrolysis. That's easy to remember also because hydro refers to water. Lysis is to break something apart. So if water comes in and hits this carbon and breaks this bond, it breaks the bond. Therefore, it's hydrolysis in that direction. So this is how we create a peptide bond. And if you have many peptide bonds, then that's called a polypeptide. And if you have, say, 40 to 1,000 alpha amino acids creating peptide bonds, well, then now we have a protein. The protein has a very important structure, and the structure can be divided in 4. Primary structure, secondary structure, tertiary structure, and quaternary structure of a protein. And it's very important in terms of the activity of the protein. Whether it's an antibody or an enzyme, whatever it is, its structure has a lot to do with its activity. The primary structure of a protein is very simple. It's just the covalent bonds. What's the order of the amino acids creating covalent bonds? So that's determined by the DNA. So it's amino acid A, then amino acid B, amino acid C. What is the order of the bonds? And that is the primary structure. The secondary structure starts to have some folding of the protein because of hydrogen bonding. So depending on what amino acids are where, then the protein can fold in a particular way. And there's different types of ways that you don't need to know about, like alpha helices or beta pleated sheets or things like that. You don't need to know those details. But that's part of the secondary structure. The tertiary structure also has to do with various types of electrostatic interactions of the various amino acids. And it could be because of hydrophobic bonding. Just like we were saying before, the interior of the protein having hydrophobic type amino acids and the exterior hydrophilic. And so the protein starts to move and shape itself in various different ways because of this interactivity. And then finally, the quaternary structure. So you can have these globular proteins that start to associate in a particular way because of hydrophobic bonding. For example, hemoglobin. Hemoglobin has the protein subunits called globin. And these units combine actually in sort of a tetrahedral type looking thing where there are 4 different components that bond to each other, are held together through hydrophobic bonding. And that's a quaternary structure. They don't tend to ask questions on the MCAT about primary, secondary, quaternary, but they do ask questions about a particular amino acid and its involvement in these structures. That amino acid is called cysteine. Cysteine is an amino acid where the R group has a sulfur atom. And when there is a cysteine, for cysteine to be in your protein, it was determined because of the DNA. There was a code for the cysteine. It was placed in the protein. Where it was placed is determined by the primary structure of the protein. Then, when the protein is folding, if there are 2 cysteine molecules, then they can bond together. And the sulfur in both of the molecules bond together, creating a disulfide bond or disulfide bridge. When there is one cysteine and another cysteine molecule that bond together, it creates what is called cysteine. I know that's not a big difference. But nonetheless, this disulfide bond helps to hold together the tertiary structure of proteins. But that's not even what they usually ask. What they usually ask is a question on the MCAT usually will come to determine whether or not you know that phosphorus is normally found in DNA, which we looked at in greater detail, of course, in biology. And in proteins, we find sulfur. Why sulfur? They don't even usually ask. But it's something that you do need to know, that relationship between sulfur and proteins. And the background is cysteine creating disulfide bridges and so on. The 2 categories of reaction mechanisms which you must understand are substitutions and elimination reactions. Now we've looked at substitution reactions, now we're going to discuss elimination reactions. So we start with an E1 reaction, which again would be elimination first order. So the rate of the reaction will depend on the concentration of one compound. So here we have a compound, it's cyclical. There are 6 carbons, 1, 2, 3, 4, 5, 6 carbons, and it's an alcohol. So it would be called cyclohexanol. And there is an acidic solution which is heated. This is the symbol for heat or energy being provided to the reaction. Of course, I put an H plus there, but once again, on the MCAT exam, they're not going to put an arrow and put a nice H plus with a juicy positive charge on it, making it very easy for you to know what would happen next. They might say sulfuric acid. They might say polyphosphoric acid, hydrochloric acid, or any number of acids. But in organic chemistry, when you hear the word acid, you should have a Pavlovian response in which right away you think of H+, because that is going to be the thing which is most reactive in that vessel, is going to be the H+ in the acid. That is what you have to keep an eye on. So here we have H plus. It is the most reactive thing. We have OH here, which the oxygen is going to be delta negative, of course, because it's attached to a carbon, which itself would be delta positive. So the electrons here would be attracted to the H plus. That would form water. Water is a great leaving group, which we've said already, and therefore that would fall off as water. Then we would have our cyclical compound with its 6 carbons, and because this falls off as water, taking along with it the electrons, because when it comes in, this H plus comes in, the charge on the oxygen will therefore become positive, because oxygen will give up its electrons to H plus in order to bond with the hydrogen, and therefore oxygen will, because it's positively charged, it will withdraw electrons somewhere. It pulls it from here, forming water, falling off as a great leaving group, and therefore the carbon here would have a positive charge, a formal positive charge. This would be called a secondary carbocation. It's secondary because this carbon has 2 R groups attached to it, and it is a carbocation because it's a positively charged carbon cation. So this is a carbocation. Now, there's no nucleophile around. There's no OH minus to jump in here and so on. So carbon is going to be looking around for electrons to draw to itself. And we know that in these other carbons, there must be a couple of hydrogens, because there must be the number of hydrogens necessary for there to be 4 bonds to each of these carbons. So this carbon must have 2 hydrogens. Indeed, this carbon must have 2 hydrogens. Well, let's look at one of those hydrogens. One of those hydrogens here would be attached to this carbon. Of course, there's another hydrogen also attached to the carbon. But for the purpose of this reaction, we'll just look at one of them. This positively charged carbon wants electrons. It looks around and it starts to pull electrons from the neighboring hydrogen. So it withdraws these electrons to itself because of the attraction of these negative electrons to this positive charge, kicking out the protein. So kicking out the hydrogen. So then we have the hydrogen being lost here. We have the OH group, which was lost at the beginning. So we have these 2 groups which are lost or eliminated from the reaction. That's why it's called an elimination reaction. And then our final product, as these electrons bond here, forming a double bond, a bond between this carbon and this carbon here. Therefore, we get the cyclical structure, and we have a double bond here. As a result of the fact that we lost the OH group, it was eliminated. We eliminated the H group, all within the same compound. The hydrogen which was used here was kicked out here, so it's regenerated as a catalyst for the reaction. It was not used up in the reaction. The rate of the reaction depends on the concentration of this compound. One compound, elimination, first order, we end up with an alkene. This particular alkene, which has a double bond, of course, all alkenes have a double bond. This particular alkene would be called cyclohexene because there are 6 carbons, so it's cyclohexene. So this was all produced by elimination, first order. Now let us look at another E1 reaction. Let us look at this compound. This compound would be called, well, there are 4 carbons, 1, 2, 3, 4 carbons. So it would be called bute. It's an alcohol, so it would be called butanol. And then we must indicate where the alcohol group or OH group is attached. So it's attached at the 2nd carbon. So this compound would be called 2-butanol. So they can say there's 2-butanol in an acidic solution. Right away, this is what you would write. So we've got H plus, the most charged substance there. It's going to be attracted to the oxygen here, delta negative. It will create water. It will fall off. It produces the intermediate, which would look like this. So I'm just not writing the hydrogens, but this is essentially what the intermediate would be. We would call this intermediate, by the way, 2-butyl, because it's missing a hydrogen at the carbon position, the 2nd carbon, so it's called 2-butyl. And this compound, this alkyl group, an alkyl group is simply an alkane minus a hydrogen. So this compound is used very often on the MCAT exam because from this compound you can do all types of reactions, including substitution reactions, elimination reactions, different orders of reactions, etc., etc. So this is very commonly discussed on the exam, this 2-butyl compound. So here we've created it. This is an elimination first order. This is the first part of the reaction, but here is where it becomes a little bit more interesting, and that is because we saw already that the positively charged carbon, here is a secondary carbocation, the positively charged carbon will withdraw electrons to itself, forming a double bond, and it would take electrons from neighboring hydrogens. And we know there's a couple of hydrogens here, we know there's 3 hydrogens here. And the question, of course, is where will it choose to pull electrons to itself? And what happens is that it preferentially chooses electrons from this carbon to come in and to form the double bond. So it preferentially does that. So basically from this reaction we have 2 possible products. One product in which it chooses to take hydrogens from here. This product would look like this. It would have this, it would have its double bond between these 2 carbons, and then you just add the number of hydrogens necessary, and this particular product would be called 2-butene. It ends in -ene because it's an alkene. 2 indicates the lowest carbon where the double bond is attached. So it's 1, 2, that's where the double bond is attached. It's 2-butene. The second possibility of a product would be if the carbon withdrew electrons from a hydrogen on the right side here and bonded with that here. And therefore we would have, as a second possibility of a product, we would have carbon, single bond, carbon, single bond to another carbon, and then this one would be double bond. And so here again we would have butene, but the lowest carbon which has the double bond is the number 1 carbon. So this compound would be called 1-butene, while this is 2-butene. 1-butene would be considered to be the minor product. 2-butene would be the major product. Why, you ask? And the reason is because this product is called di-substituted, meaning the functional group is the carbon-carbon double bond. This is the functional group for this particular compound. And at the functional group, there are 2 alkyl groups attached. One on the right, one on the left. 2 alkyl groups. So it's called a di-substituted compound. It has 2 substituents attached at the functional group. It's di-substituted. Here we have the double bond, the functional group, and there is only 1 alkyl group. It happens to be ethyl. It happens to have 2 carbons, but it doesn't matter. There's only 1 alkyl group attached to the double bond. Therefore, it is mono-substituted. Well, when there is more substituents, it helps to stabilize the double bond. And therefore, this compound is more stable because it is di-substituted than this compound, which is mono-substituted. And therefore, this compound, 2-butene, would be the major product. Now let us look at E2 reactions. We will now look at elimination second order. So that's an E2 reaction. It is called elimination because in the original organic chemical, we will see that a couple of atoms will be eliminated, and that will reduce it into a double bond. Then it's called second order because this time the rate of the reaction will depend on the concentration of 2 compounds and their interactions. So this particular compound, well, we have 1, 2, 3, 4 carbons, so it's bute. It's a alkane, it's a hydrocarbon, and we have bromine at the second carbon position. So this is 2-bromobutane. This is a very popular MCAT chemical as well because there are many different types of reactions that can occur using this particular chemical. So that's 2-bromobutane. Here we have potassium with a base. Now, if that base happened to be OH minus as a base, then I think you would say, as your first suggestion as what would happen in this reaction, would be that this carbon is delta positive, that's delta negative. So if this was OH minus, then the OH minus would be attracted to the delta positive carbon, hit this carbon, knock out the bromine, and then there would be a transition state in which when the OH minus is coming in, the bond with the bromine is being broken. Therefore, OH minus has to come in from backside displacement. That would create a secondary alcohol, 2-butanol. The molecule would be inverted because the OH minus would have to come in from behind to knock out the bromine. So I believe that at this point, that's what you would suggest if this base was OH minus. And that would be the most likely scenario. However, if this was a big, bulky base, and it was a huge base, therefore it wouldn't be so small and nimble like OH minus to be able to come in here and bond. Because don't forget, there's a CH3 group here, there's an ethyl group here, they occupy a certain space. So it has to be a particular size to be able to get in here and to knock that carbon and to knock out the bromine. But if it was a large, bulky base, for example, consider the following. Instead of OH minus, consider O, C, CH3, CH3, CH3 minus, as opposed to just OH minus. Clearly, this is a big, bulky base, and you should be able to easily name this base. There are 4 carbons, 1, 2, 3, 4. So you know the word but is going to be in there somewhere. And this is a tertiary carbon because there are 3 R groups attached to it. So we know the word tert or T, just the letter T, would be included in this. So there's a but and then there's the O minus. Well, we know that this is called hydroxide. This is the hydroxide. So this is called tert but oxide. So tert butoxide or T-butoxide. So this is a very big, bulky base. And a big base is not going to want to engage in a nucleophilic reaction, which would be very easy for a OH minus. A big base, and bases are substances which like to attract or to take on a proton for itself. So it would like a proton. It doesn't want to do a nucleophilic reaction for it. So because it's big and bulky, it will preferentially take primary hydrogens. In other words, it would preferentially take, see, this is a primary carbon position. So this, because it only has 1 R group attached to it, this has hydrogens here. So the big bulky base would like to just pluck the hydrogens, sort of like grapes or something, and it would rather take them where they're easiest to take. So it would rather take them right from here. And if this big bulky base was to take a hydrogen from this carbon, what would be the charge on the carbon? It would be negatively charged. Because if you take a proton, if the base takes a proton away, then the charge on the carbon would be negatively charged. And this carbon over here is delta positive. So if this is negatively charged and this is delta positive, there would be a great force of reaction because it's an intramolecular reaction. So this negative charge will quickly knock and hit this delta positive carbon because of the opposites attracting. And then this carbon can only be bonded 4 times, so somebody's got to leave, so this bromine would leave. So the negative would come in here, bond here, and then the bromine would leave. So then we would have as a major product carbon, 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 double bond to carbon. So this, in fact, as our major product, would be a 1-butene. So in other words, it occurs in such a fashion that this is mono-substituted. Why? Because of the mechanism of reaction. It's not as if we had a choice that it could go this way, it could go that way, and it doesn't really matter, so it only depends on the stability of the product. No, this time it really did matter, the mechanism of reaction, because it's a big bulky base. It's very easy for it to pluck off hydrogens over here, and then we have this reaction. Now you might wonder, would it pluck off hydrogens from this carbon over here? No, because if it took a hydrogen from this carbon, we would have a primary carbanion, which is a negatively charged carbon. So it's a primary position carbon. But the problem is that once this carbon is negatively charged, it can't do anything with its negative charge. It can't give it off somewhere. It would be sitting there with a negative charge. It can't give it to this carbon because this carbon doesn't have a leaving group. It has a couple of hydrogens. So it would be stuck with a primary carbanion. Extraordinarily unstable compound. So that would not occur. Can this big bulky base take some hydrogens from this secondary position? And in which case, if it took it from the secondary position, this negative charge could bond, make a double bond between these two carbons and knock out the bromine. Indeed, it can do that. It wouldn't do it very often because it's much easier to take it from the primary carbon. So, but every so often it might take one or two from this particular position, and therefore we would have this as our product. We'd have carbon, carbon, then double bond, carbon, carbon, because the double bond would form between here and bromine would be kicked out. Either way, these are elimination, second order reactions, and producing either 1-butene, which would be our major product in this case, or 2-butene. There is also a hydrogen on this carbon right here. Is it possible that this big bulky base would pull off a hydrogen from this carbon? No way. Once again, it's the same reason as for this particular position, and that is that, or similar reason, because you would have a secondary carbanion and there would be nothing to do with the negative charge. You couldn't get rid of it because this carbon has a leaving group, but it can't dish off the extra electrons to one of its neighboring carbons, and therefore it would be stuck with this extra set of electrons. So that would not occur for this hydrogen to be removed, nor for the hydrogens over here to be removed. Those are extremely improbable events. But to produce this and this is very probable, and this is less probable. Now that we've seen how to make an alkene, we will now look at reactions with alkenes. And so here is an alkene because there's a double bond to the carbon. And so, well, let's name it. This alkene, the longest chain, has 1, 2, 3 carbons. So it would start with prop, end with ene, so it's a propene. And then at the second carbon, there is a methyl group. So this would be called 2-methylpropene. And this is an alkene plus an acid. So the alkene, as its functional group, it is the double bond. It is the most reactive site in the alkene. The reason is this is an electron-dense center. So here is an acid, HBr, could be HCl or whatever. Now, as soon as you see the acid, you should be thinking of H plus and Br minus. H plus is something which is going to be very attracted to electrons. And in fact, when we looked at our definitions, our basic definitions for organic chemistry, that was our definition of an electrophile. An electrophile is something which seeks electrons. It is literally electron-loving. So hydrogen is electron-loving. And here is an electron-dense center. So hydrogen will add to the double bond, and therefore it will add to either this carbon or this carbon. The question, of course, is which one will it add to preferentially? Well, if hydrogen were to add to this carbon, then it would withdraw electrons to this carbon so that it could add here. Therefore, this carbon would end up being positively charged. If this carbon is positively charged, therefore we would have a primary carbocation, and we've already seen that that's very unstable. However, if the hydrogen were to add to this carbon, withdrawing electrons in this direction, Therefore, breaking the bond and withdrawing in this direction so the hydrogen can add to this carbon would become positively charged. And if this carbon becomes positively charged, well, therefore, we would have a tertiary carbocation, and obviously that it would be stable. So if we have the tertiary carbocation, that would be stable. That is the most likely reaction. So we would have CH3, we'd have carbon, we'd have CH3, we'd have CH3 here because the hydrogen added to it. This would be positively charged. And then because Br minus would be floating around in solution, not up to anything much, but it would see a positive charge and therefore it would bond to this. And so then we would have a bond like so. And this would be our product. This product, which occurred using the most stable intermediate, would be called a Markovnikov product. This would be called our Markovnikov product because it did come through the most stable mechanism. The anti-Markovnikov product would be the product that would occur if the H plus had added to this carbon at the beginning of the reaction, creating a primary carbocation, not very probable, and then the Br minus adds to that. So then our anti-Markovnikov product would be carbon here, CH3, the carbon would have had the hydrogen add to it. Then we'd have our CH2, and this is where the bromine would end up adding because that's where the positive charge would end up. So this would be our anti-Markovnikov product. This would be our Markovnikov product. Now, Markovnikov himself defined a Markovnikov product as follows. It is a product that occurs when you have an alkene plus an acid. The hydrogen would add to the least substituted carbon preferentially. So that's Markovnikov's definition. The hydrogen would add to the least substituted carbon preferentially. So in this particular situation, this carbon has 3 substituents attached to it, 3 ligands, and this carbon, well, it just has 1 because the hydrogens are not considered to be substituents. And so this one has the least substituents compared to this particular carbon. So that's one way of looking at it. But students don't memorize it that way. Most students memorize it. But Markovnikov's rule is that the hydrogen adds to where most of its buddies are. In other words, hydrogen will add to the carbon with the most hydrogens, and that is exactly the least substituted carbon. So this hydrogen would preferentially add to this carbon because this carbon has 2 hydrogens attached to it, whereas this carbon has no hydrogens attached to it. So this hydrogen would preferentially add to this carbon. So then preferentially, because it adds to this carbon, producing CH3, this carbon becomes positively charged. The Br lands in there and bonds here. So this is the Markovnikov product. We will now look at another mechanism or reaction involving an alkene. So here we have 3 carbons, so this must be propene. And this is in solution. Now, on the MCAT exam, as I've mentioned already, they're not going to put a nice H plus on an arrow and water over here, making it clear what's going to react with what. But they may say something like propene is in an aqueous acidic solution and blah blah blah, and give you a bunch of other information which is irrelevant. As soon as you hear propene, you write it down. Aqueous, water, solution, which is acidic, proton, that's what you think of. Then you look at what is the most reactive thing in the substance. It'll be the most charged element or species, and this is H plus. So we have the double bond, which is here. So that's going to break up as it's attracted to the positive charge, because this is the electron dense center. And once again, where does the proton preferentially add? Well, you can use Markovnikov's rule, saying the least substituted carbon, which would be this carbon, because this carbon, compared to this carbon has this substituent, which is extra, and this carbon does not. Or you can just use the student's rule, which is hydrogen will add where its buddies are, preferentially, and so it has two friends here, it only has one here, so the hydrogen would rather add to this carbon. So then you would get a secondary carbocation. So you would have 2-propyl, you can call it 2-propyl, as your intermediate. And then you would have this delta negative oxygen with its lone pair of electrons, and therefore this is the most charged species at this point. This is going to be attracted to it, as opposites attract, to the carbon. When oxygen gives up its electrons to the carbon, the oxygen would be positively charged. It will have 3 bonds. When it's positively charged, it will want to draw electrons to itself because oxygen is an electronegative atom. And so it will draw electrons, it will kick out one of its hydrogens, a proton, thus it regenerates the catalyst of the reaction. And then we would end up with this as our product, which is OH group attached to the carbon, and then this carbon. So this would be called a secondary alcohol. You can also call it 2-propanol, and this would be our product. Now this would be called our Markovnikov product, as it occurred through the most stable mechanism with the hydrogen adding to the least substituted carbon. Had, for whatever reason, the hydrogen added to this carbon and created a primary carbocation as an intermediate, then what would happen is the OH group would attack this carbon and the OH group would add to that carbon, and therefore we would have as a product carbon, 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 OH. And so this product would be a primary alcohol. It would be called 1-propanol, and this product would be called an anti-Markovnikov product. So this is our Markovnikov product, this is our anti-Markovnikov product. Now, it is important to understand mechanisms of reactions, because even when we say that something is improbable to occur, that means that it still occurs, but it's unlikely. And the MCAT can actually play with that. In other words, they can say, in this, which of the following is the product? If you look at the answers, if you have the major product and the minor product as possible answers, obviously you choose the major product, because in the MCAT they ask you to answer with the best answer. What is the best answer to the question? And so if you have a choice between a major product and a minor product, then you choose the major product. However, sometimes on the MCAT exam, what they'll do is they'll ask you a question on organic chemistry and the major product is not even among the possible answers. The only thing that would be there among the possible answers sometimes would be the minor product. In other words, they want to know whether or not you know the 2 possibilities for a given reaction. And so here you can clearly see how you can have one or the other reaction. Even though you know that one of the reactions is improbable, you know that it is possible to have an anti-Markovnikov product. So if you had a choice between what is the correct answer, you would go with the Markovnikov product. If the Markovnikov product is not an option, then you take the anti-Markovnikov product as your answer on the exam. Finally, something in life which is truly free. Free radicals. Free radicals are in so many different aspects of human life. Everything from taking life, from giving life. In fact, free radicals are found, they can be created by ultraviolet light in the skin, in the cells, and these free radicals, they're so highly reactive, so unstable, they can actually cause permanent damage to DNA and therefore cause skin cancer. Just like it can take life, it can give life. It has been found that free radicals are used by sperm in order to blow a hole in the envelope of the egg in the act of fertilization. Free radicals are also found in your breakfast cereal. A large hindered free radical called BHT is found in the packaging of most breakfast cereals. It sort of just hangs around in the packaging, waiting for free radicals to be formed in the cereal itself. Now, free radicals in the cereal will change the cereal, and therefore it will change the taste. It's what we call staleness. And so by having this free radical, hindered free radical around the cereal, it's able to mop up the free radicals that are formed in the cereal, and it's able to keep the cereal fresh for a longer period of time. So how do you make a free radical? Here is a substance. As we know, X stands for a halide, so this could be Cl2 or Br2 or whatever. And here we have HF. And from your knowledge of physics, you should immediately recognize HF as energy, because of course E equals HF. So we can represent energy, light energy, as HF over the arrow. So when this substance is exposed to light energy, we can create a free radical. And the free radical is going to be symbolized by X dot. So we have 2 here, so this would be 2X dot. So this is a new substance. It's not X negative, which we've seen before, which when we see a negative or a plus, a formal charge on a substance, we know that represents an electron pair, either an extra electron pair when it's negative, or when it's positive, it's missing an electron pair. But when we have X dot, that means a single, unpaired electron. That is a very unstable situation. So these compounds are highly reactive because they're unstable. So this particular step, when we take a compound which has no free radical, and then we apply energy and we create free radicals, this is called the chain initiation. Once we have a free radical, many different things can occur. One of the possibilities is that we can get propagation of these free radicals, meaning a domino effect where one free radical creates another, etc. For example, let's say that we had an organic chemical. This organic chemical will symbolize as RH. So it's like an alkane. So it's RH. So there's just an H hydrogen which is attached to the particular alkyl group, forming an alkane. Now, if you were to add a free radical, which we have just created, this free radical, being so unstable, will just tear one of the atoms off the alkane or off the organic chemical. Obviously, this is going to change the organic chemical from its original form. So this will just tear it right off, and then what we would have is we would have R as a free radical, and then we would have plus HX, which would be the new compound, as the X group tore the H off and left an unpaired electron on the R group. Likewise, this R group, which has now been created, which is a free radical, if it is exposed to the original compound that we have, this R group can therefore rip that off, and we produce another chemical plus another free radical. Therefore, our free radical has been regenerated. And then we've changed the compound. Whatever compound we had originally has changed. In nature, when chemicals and molecules are exposed to energy, the sunlight, many of these types of molecules and substances can deteriorate, can rot, and there's many of these processes are caused by free radicals which tear apart organic chemicals and therefore change the original substance. The fact that we start with a free radical, we end with a free radical, these kinds of steps are called chain propagation steps. So we have the initiation up here, we have the chain propagation over here, and then in the third of the possibility of steps that could occur with free radicals, we can have free radicals, one plus another, producing new compounds. So this would be called a chain termination step, in which you have a free radical plus a free radical creating the end of a chain. And of course, there are many different possibilities of these free radicals that could be added to each other, creating a chain termination. So these are the different ways in which free radicals can be generated, can be propagated, and can be terminated. We are now going to look at a series of reactions called redox reactions. Redox reactions are reduction or oxidation reactions. You do not need to memorize the mechanisms for these reactions for the MCAT exam. So unfortunately, unlike what we've been looking at throughout the organic chemistry, this is a section where you sort of need to memorize what happens during an oxidation or during a reduction in terms of what types of products you would expect. Some students like to memorize that during an oxidation, it's like adding oxygens. But that has to be specified, and you'll see how. Some students like to memorize that reductions, it's like adding hydrogens, and we'll specify and see how shortly. First, a couple of examples. Here is KMNO4. KMNO4 is a very popular oxidizing agent. It can be used in two different ways, either under mild conditions. Mild conditions means neutral pH and mild temperature. Or KMNO4 can be used under abrasive conditions with OH minus and heat, symbolized by delta. So these are different conditions. There is an oxidizing agent called CrO3, and CrO3 is a mild oxidizing agent, and therefore it could replace KMNO4 as an oxidizing agent in many different reactions. Nonetheless, KMNO4 is the most popular oxidizing agent that is used. This particular compound, you should consider naming these compounds before I mention them, but this one has 5 carbons, and there is a double bond here, so this would be called cyclopentene. So when it is oxidized under mild conditions, the product would be as follows. Now, this triangle, of course, is a solid triangle, so that means that it's coming out of the plane, and this is oxidized in this way. And then in behind, we would have some hydrogens, which we don't even really need to draw. But nonetheless, just to be more specific, here we see our product. This is the way it would be oxidized. What is interesting about KMNO4 and the way that it oxidizes on the same side of the molecule. Meaning, if you note here, both of these OH groups, which are a product of the reaction because KMNO4 oxidized, remember, some people remember it as though oxygens are added as a result of oxidation. Therefore, but both of them are added on the same side of the molecule, meaning both of them are above the plane of the molecule indicated by these solid triangles. If you should consider how you would name this particular compound. This compound would be called, it would be a diol because there are 2 OH groups. It would be called cis because both the OH groups are on the same side. It's not trans where one OH group is on one side and the other is behind the molecule. So it would be 1,2-cis pentane diol. Over here we have KMNO4 under abrasive conditions, and this would be, of course, cyclohexene. And under abrasive conditions, KMNO4, instead of just oxidizing up to a diol, it actually breaks the ring. So the ring is broken, and we get COOH. And the same thing up here, COOH. So we see that the ring is broken. The carbons are not only oxidized with an OH group, they're oxidized with a carbon with a double bond oxygen. So that's 2 levels up. There's this level, there's the level with the OH, and then there's the level with the COOH, which is the second level up under abrasive conditions. COOH you should recognize as being the functional group for organic acids. And so this functional group for this particular organic acid, because there's two organic acids, just like this is called a diol because there's two alcohol groups, there are two acid groups, so this is called a diacid. This particular compound happens to be called adipic acid, but that you would not have to memorize.